Hi everyone, in this video, this will be our last Riemann integration video before the Riemann-Lebesgue theorem, so hang with me. I've just got a few more terms to introduce, and we're going to prove a small lemma with a discontinuous function that will serve as a proof outline for the Riemann-Lebesgue theorem in the next video. So we're getting into the interesting stuff. So I'm going to introduce a few terms, oscillation and Lebesgue measure. So first, definition is set oscillation, or saucillation, if you like. That is a typical setup, bounded function on a closed interval, and the set oscillation is defined over a subset of our domain A. So domain is I, subset A. We feed that in as an argument, and it is the supremum of the difference between f of x and f of y over any 2 points in the domain. So we don't care if they're close, okay? Oscillation, we care if they're close, and we use that definition to define oscillation. So that's why we use set oscillation. Most authors will do this as not a separate term, but I just like to do it for clarity. Same setup, f is bounded on closed interval. It's oscillation at a point x. So this is local now. So we feed a point as an argument. It is the lim sup of the set oscillation of f over a small open interval around the point x. This limit will actually exist, so you can drop the lim sup. It's basically supposed to be the worst case scenario. That's why I put lim sup there. So just as an example, if we take the identity f of x equals x, and we look at 1/2 to 3/4, and we say, what is the set oscillation on that point? Then it's not very small. It's 1/4, because I can just take the maximum difference here, calculate that height, it's 1/4. Don't care how close they are. Whereas the oscillation, let's say at x equals 1/4, I take a sequence of smaller and smaller subintervals. I take the maximal difference over the domain, and I keep taking smaller and smaller intervals, and I take the limit of the expression that I get at each small subdomain. In that case, when I take that limit, I get 0, because that expression is just 2h. And just keep in the back of your mind, a function is continuous at a point if and only if its oscillation is 0. So you can think here, if I had a discontinuity here, then as I take the small subintervals, on this left-hand side, I'm always down here. On the right-hand side, I'm always up here somewhere. So I have a positive distance there. So the oscillation would be strictly greater than 0 and would be discontinuous. It's an if and only if statement. That'll come in later when we prove the Riemann-Lebesgue theorem. So now on to my last definition I'm going to introduce before our lemma, and that is Lebesgue measure. So recall a few videos ago we talked about measures. Here are space, our measure space. Our point set is I, and we need to define a sigma algebra. I'm going to define it below. This is the following. It's a countable union of open intervals. So you give me a sequence of open intervals, and I union them together. That's in the sigma algebra, because countable unions are closed under, or sigma algebras are closed under countable union, but also they have to be closed under complement. So I also have to, in my definition, throw in all the complements of sets that look like this. And then if I union them together, that gives me an arbitrary set. And then all these points are in the in our original point set. Okay, so now I'm ready to define a specific. So we have a specific sigma algebra that I'm giving you, and now I'm going to give you a specific measure that we're going to call Lebesgue measure. And it's just defined as follows. If I give you an interval, I'll just take the right endpoint and the left endpoint and subtract them. Otherwise, it's the empty set. I guess I'll write that. And the measure of the empty set is 0. Because when B is less than A, that's the empty set, but then you get a negative value. It doesn't make sense. So if I'm inputting the empty set, I get 0. So most authors will just write this and be done with it. Just to clarify, what they're saying does make sense, because remember that a measure satisfies this sum disjoint set sum property. So implicitly what that means is if I give you open intervals here that whose intersection are empty when m is not equal to n, then the rule tells you, okay, well, they're disjoint. I told you m is a measure, which implicitly tells you that that's just this sum here, and then I already gave you the formula for an open interval. So there it is, and I give you the measure. So that's how you calculate it. So just as a quick illustration, if I take this interval here and say this is 5/8 to 7/8, call that A1, and let's call that 1/4 to 1/2. So this distance is 1/4. This distance is 1/4, A2. So the measure of A1 union A2 is 1/4 plus 1/4 is 1/2. So that's all there is to it. And then just recall that a typical set can be not just finite unions, but tons and tons of these, and I can include their complements. So if I take the complement of this blue set here, that is really that closed interval unioned with that closed interval. And then if you do set manipulations, you can actually get closed intervals as well. So just think of these as really, I could also write this as that being a closed interval, or open on one side, closed on the other, closed on the left, open on the other, or just closed on both. So those types of sets, basically, closed and open interval combinations of every sort is really what we're looking at when we're talking about those, and unions and intersections of them. So now we're ready for the main lemma here. So all we're saying here, f is bounded and continuous pretty much everywhere except for one point, y naught, that is on the interior of our domain. Then f is still Riemann integrable. That's what we want to prove, which is intuitive because in Calc 1, sometimes you calculate things like that. There's one discontinuity and you have to split it into two parts. That's basically all that's going on here. So this will seem like a somewhat technical construction here. It's not too bad, but we're just going to go ahead and plow through it, and then I'll show you guys a picture. Pn is x naught to x2n plus 1, which is a partition with xn equal to a plus y naught minus 1 over n minus, let's put this on the, so this is just n over n, typical of seeing. So I've now shifted over by 1 over n. And y naught plus 1 over n plus n minus 1 over yeah, that's correct. Okay, y naught plus 1 over n. No, not b minus y naught plus 1 over n. N plus 1 less than or equal to n less than or equal to n plus 1. So I figured that out ahead of time. All that we're doing here, it's a bit of a construction, but it's not too bad. All that I want is y naught. So remember, y naught is our discontinuity. So all I'm doing is I'm starting at A, and I'm taking a uniform mesh all the way up to y naught minus 1 over n. Then I'm just taking a very coarse, well, possibly, it's not very coarse, it's 1 over 2n, length 1 over 2n. I'm taking that distance, y naught is right in the center, and then I'm slicing another uniform mesh on that side. The reason why I'm doing this is because it's going to make the remainder of the theorem easier to do, because I can guarantee that this discontinuity doesn't end up on an interface, because then I have to worry, okay, well, that part of the mesh shares the discontinuity with this part of the mesh and so on. So I'm cinching off the discontinuity by just doing that to that, so that I don't have to worry about it. So okay, so our ultimate goal here is to simply look, well, what's the difference between the upper sum and the lower sum? Because if that gets small as n goes to infinity, then we get Riemann integrability. So I'm going to split this into 2 parts, or into 3 parts. So I'm going to do this light blue. Yeah, let's do this. So just to shorten some things. So you can convince yourself that this is true. If I want to take the maximal difference here, I just take the supremum minus the infimum, and that should give me the set oscillation. So we can rewrite this now. I'm going to call this alpha sub n. That is the mesh size over here. You can do the calculation. It's y naught minus 1 over n minus a divided by n. If you want, but I'll just call that alpha sub n. You can do similarly on the other side of the domain. It's not too important. The point is that goes to 0 as capital N goes to infinity of xn minus 1 to xn. Okay, let's just do this. Okay, so then plus, I'll do the right-hand side in green. So this is n equals n plus 2 to 2n plus 1. I'm going to call this beta n. Again, beta n is b minus y naught plus 1 over n over n. It's that distance. S oscillation of f, xn minus 1 to xn. And then in red is the super interesting part. That's where the discontinuity lives. So that mesh size is going to be, let's see. Oh, it's just 1 over 2n. It's 1 over 2n times the S oscillation, the set oscillation of f on the interval y naught plus 1 over n. Okay, so I'm going to call this term GL of n. I'm going to call this GR of n. And I'm going to call this GC of n. Okay, so L is left, R is right, C is center. Okay, so note the limit as n goes to infinity of GL of n is 0. F is continuous on A to x naught for all for all n large enough. This is 0. same on x naught plus 1 over n to b. Because I cinched y naught off. Y naught is definitely not in any part of the subdomain. So those two terms are essentially trivial to work with now. So now all we need to do is show that this limit is 0. Well, this is a product of two limits. So it splits, assuming that we know each limit exists in this context. They do, because f is a bounded function. So certainly its S oscillation is bounded and will be a decreasing sequence. So, or non-increasing if you like also. So its limit exists. Okay, so then this is 0 times, I don't know, we don't have to call it lambda. This is the oscillation of f at y naught, okay? And again, f is bounded. That's less than infinity because f is bounded. Okay, so in this context, we didn't actually need to be this tight, right? This is the oscillation. We could have just said, oh, there's a bound to m, multiply it by 2, and we're fine. But when we prove the Riemann-Lebesgue theorem, we're going to need this oscillation. We're going to need to be a little bit more fine-grained than just bounded. That's why I wanted to do this. So this is equal to 0. That implies L of f equals U of f. And that proves Riemann integrability. So now we're going to go from just one discontinuity to possibly an uncountable number of discontinuities here. And this oscillation object and Lebesgue measure are what are going to be able to give us the tools to characterize Riemann integrability. And so in the next video, we'll finally get to the Riemann-Lebesgue theorem. And thank you guys for watching.